forward on this computer. And we'll stop those beepings. Sorry about that. Any questions before we get started? Okay. No. Any questions? Just put it in the chat. I'll try and get to it. You all saw my notes about the projects. If you didn't see the note, I post the notes both on Moodle and on WebAssign now. So you should see the announcements every time you go to WebAssign and do your homework. And you should also have gotten an email with my assignments. Let's get started. So that would be, nope, Keynote. Okay, we have a test 1 week from today. So we've got lectures on Tuesday, and then we've got the exam on Thursday. The exam will be like the previous exam with 2 exceptions. The first exception is you only can take the test between 10 a.m. and noon. Sorry about that. And the second is it's 1 through. When you answer a question, you cannot go back. Okay. The exam is on well, the last few lectures, but it's on chapters 6, 7, 8, 9, 10, 11, and 12. And I have already posted this file on WebAssign under resources, and it lists all the topics that are covered in the exam 3. Any questions about the exam? Put the questions in chat, please. Okay, so I want to finish up with, oh, by the way, one issue that's been bothering me all night. We're not, as instructors, as professors here, we're not allowed to be political. And normally I adhere to that because everybody has their own beliefs. But there's 2 things you need to think about. One is, do you believe that there does exist an objective truth, that decisions should be made based on evidence? Decisions should be made on the best evidence that's out there. And the second is, do you believe that a country should be governed by the people itself? In other words, should we be a democracy? We were the first democracy, and we were the most successful. And so the most important thing you can do this semester is vote. Every single one of you needs to vote. Anyway, let's go back to astronomy because we've got a lot to cover today. So a student asked a question last time about why is the spectra the shape it is? And I kind of mumbled an answer, but I want to answer a little bit more fully here. Just to refresh your memory, this is the black body spectrum. We call black body or thermal or continuous spectrum. And the spectrum, we don't give you the full equation for the shape, but we do give you 2 important equations that you need to know. One is that the wavelength is proportional to 1 over the temperature. And so here the wavelength decreases as the temperature increases. That's the Wien law. And the second is the Stefan-Boltzmann law, which is the total energy, which is the total amount of area under this curve, goes up as the temperature to the 4th power. So as you go from 3,000 to 6,000 degrees, the area here would be 2 to the 4th, or what's 2 to the 4th? 16 times the area that's under there. Why is that? Why is it the shape that it is? Let's go back to the simulation you've seen before. Where as the temperature goes up, the color goes from red to blue and the area goes enormous. And why is that? It's that way. I can't go into the quantum mechanical details, but I can walk you through something that will make sense to you, I hope. So here is a program. And what we have is a box that contains a bunch of balls. And when we talk about a black body spectrum or a thermal spectrum, what we're talking about is something that's really thick, such as you. You are really thick, and if there's something inside you that's produced light, little photons, it's going to take a long time for that photon to get outside you. It was take thousands of bounces. And so these balls are going to be bouncing around inside a box. They're not going to be able to escape the box. And so this emulates what happens inside really thick objects. And these are literally billiard balls in the simulation, but they could just as easily be photons, little bundles of light. And the simulation starts, why did that go? Why is that down there? There we go. You see this graphic here, and what this graph is along the x-axis is the velocity of each of the ball. And so as we start the simulation, all the balls have the exact same velocity. And what's happening is as these balls collide against each other, they will exchange energy. Some will gain energy, some will lose energy. I click again, and you see that blue curve. That blue curve is based on a quantum mechanical calculation of what we think, actually in this case, it's just a classical calculation of what we think the eventual distribution of the ball velocities will be. So we start with all the balls with the same velocity, and we think we're going to end where we're going to have balls that don't have a lot of velocity, we're going to have balls that have a lot of velocity, and we're going to have most of the balls will have some intermediate velocity that's related to the main velocity there, okay? So this is what we think is going to happen. So we're going to run the simulation. The simulation does not have this curve built into it. All the simulation does is it moves these particles forward, and when the particles collide, based on how they collide, it will exchange the energy. Sometimes one ball gets more, sometimes one ball gets less. Watch what happens. So these balls bounce around. You can see this cyan ball there, and that just shows you an example of the path of a single ball. And notice it just bounces around from various directions as it's impacted. So this emulates what happens inside thick objects, and that's why thermal radiation, continuous radiation, black body radiation, is only emitted from objects that you can't see through, such as us. And as you can see, it's eventually going to the shape where we got slow balls and we got fast balls. So in fact, let's run this a little bit faster here. And instead of a rate of 15, we'll go to a rate of 150. And now we'll run it really fast. And watch what happens. Again, this shape is not built into the simulation. The simulation just has balls bouncing. So this is why the black body spectrum is what it is. We have light that's inside thick objects such as the sun, such as us, such as anything that's a natural object. And the light bounces around, and some of the photons gain energy, some photons lose energy, but the end result is this curve, okay? Which is true of every thick object in the universe. Every thick object in the universe emits electromagnetic radiation, and every thick object in the universe will emit radiation of this exact shape. Now, objects that are thin, such as clouds we're about to talk about, the emission spectra and the reflection spectra, they're different because then you're not going to have the chance to bounce around, and we'll be talking about that in a little bit. Anyway, I just wanted to bring that up, okay? And again, remember the energy goes as sigma to the fourth power, this constant, which you don't need to worry about, but the total energy of that black body spectrum increases as temperature to the fourth, and that's the total energy per unit area there. And so the total luminosity, as we covered last time, is equal to the surface area times that t to the fourth. So the luminosity is equal to r squared t to the fourth. And so that has, oh shoot, I'm not sharing. Someone should have told me. Okay. There we go. Sorry about that. Oops. So the luminosity goes as 4 pi r squared t to the fourth. Is the chat working? I don't see anybody with the chat. Say hi, please. Can someone say hi? Ah, great. Okay, it's working. So we have, as we talked about last time, the luminosity goes as 4 pi r squared sigma to the fourth. I didn't show you the simulation last time because Apple changed the way it deals with Flash. I found a workaround, and here is the simulation I wanted to show you. Let me share. Okay, and this will put some meat in the bones of that L equals 4 pi r squared t to the fourth. And here's that same equation where they've solved for radius. So L equals r squared t to the fourth. Well, then r is equal to the square root of L over t squared. Okay. And so here is the HR diagram that we talked about last time. We have luminosity on one axis and we have temperature on the other. Now, instead of temperature, we could say spectral type, O, B, A, F, G, K, M. But we'll just use temperature. Or we could talk about color, okay? So temperature, 40,000 degrees, 2,300 degrees. And luminosity, notice luminosity could also be absolute magnitude, okay? But I found absolute magnitude a pain. So here's luminosity. And again, as we talked about last time, luminosity is a logarithmic curve. We go from 1 solar luminosity to 1,000,000 solar luminosities down to 1,000th of a solar luminosity. And then these diagonal lines that start up high on the left and go down to the right, because the L equals 4 pi r squared, good morning, r to the fourth, we can solve for the radius here. So notice what happens as I move to a higher temperature and I keep the luminosity the same, okay? So the luminosity stays at 1. So this star here, this blue star, has 1 solar luminosity, but because it's at 22,000 degrees, it has to be much, much smaller. Again, because that L equals r squared t to the fourth. If the t goes up, for the same luminosity, the r needs to go down, okay? And consequently, if I go up in luminosity, but I keep the temperature the same, we're going up. Notice that the size of the star has to increase enormously, okay? So here, let's show stars. There's some stars, and let's show some luminosity classes, okay? So here, when we go down to white dwarfs, you know, white dwarfs will have similar temperatures to the sun, but look at the luminosity, 0.00031. Okay? And when we go up to supergiants, literally supergiants, look how big this puppy is. It's 1,000 times the radius of the sun. And remember, the sun is only 100 times the size of the Earth. So these are mind-blowingly large stars. Okay, so this simulation shows you that there is a very strong relationship between luminosity, the temperature, and the radius, and you can just play around with this. Okay, and that L equals 4 r squared t to the fourth is incredibly powerful. That means if I know the luminosity and I obviously know the temperature, I can tell you exactly what the size of that star is. Can a planet be as big as a star, or can a star be as small as a planet? Yes to both. So for instance, there are many stars that are the size of Jupiter. And can a star be as small as a planet? Yes. So when we get down to, so remember I said that the Earth is 1/100th the size, the radius of the sun. Well, 1/100th is 0.01. So in fact, this 0.01 curve is the size of the Earth. So in fact, essentially all white dwarfs, which we'll be talking about in a future lecture, are the size of the Earth. How bright is a full moon in terms of solar luminosity? I'll have to look that up. Let me write that down and figure it out. Okay. What would happen if we launched a person into the sun? What do you think, Joseph? It would not be a good day. So for instance, I used to work for Johns Hopkins Applied Physics Lab. And Johns Hopkins and AP, what we call it APL, Applied Physics Lab, made a satellite called the Parker probe, which is currently in orbit around the sun. And it is going to get inside the sun's atmosphere in the next couple of orbits. And when it does so, nothing can be exposed. It's got a huge heat shield. And if the solar panels ever even kind of dance outside that heat shield, they will be fried instantly. So, and that's long before it gets anywhere close to the sun. So we feel the sun, the light from the sun comes to us, and the sun is at 5,800 degrees. And so the effective temperature of the radiation that comes from the sun is 5,800 degrees. And if we had no way of cooling ourselves, we would be at 5,800 degrees. Like you're inside an oven, except in the oven, instead of being 400 degrees, is 5,800 degrees. The reason why we don't burn up to 5,800 degrees is because we're rapidly cooled. We're cooled by the air hitting our skin. We're cooled by, we're radiating away our black body radiation from our body. If you're close to the sun, there's really no effective way for you to get rid of that heat. And so you can't radiate it because the amount of 5,800 degree radiation that's hitting you is much, much greater than you can radiate away. And there's no cold breeze hitting you to cool you down. And so you heat up to 5,800 degrees. And I don't know about you, but I would find 5,800 degrees very uncomfortable. Would not be a good day. Okay, so let's go back to, actually, let's start with today's lecture, which we haven't even started yet. So today we're going to talk about the interstellar medium and star birth. And there's a very little math in today's lecture, but there's a lot of detail, and it's very irritating detail. And in fact, the book will have a lot of irritating detail. I've not included everything that's in the book. What I've tried to do is organize it in a way that's easier to follow. I'm not completely convinced I did it right, but this is the best I can do. We're going to revolve around this picture here. And this picture includes everything we're going to be talking about. We're going to be talking about in the interstellar medium, we're going to be talking about dark dust clouds. We're going to be talking about emission nebula, and we're going to be talking about reflection nebula. And there's lots of other things out there in interstellar space, but those are the three things we're going to be talking about today, and those are the three things that will be on the exam. Lots of the other stuff, molecular clouds, we're just not going to cover, and it's not going to be on the exam. So we're going to, today we're going to talk to you about the interstellar medium. We're going to talk about cold dust clouds, emission nebula, reflection nebula. And then at the end of the lecture, we're going to go on to the next chapter and talk about stellar nurseries, where stars are born. A Star is Born. That was a good movie, by the way. And then we'll talk about how stars and stellar birth. Okay, so introduction to the interstellar medium. If you didn't live in North Carolina, if you lived at a place where you could actually see the Milky Way galaxy, and this is a picture from Earth of this band of what it looks like clouds across the sky. It's very dim, and if you're out west with no lights around you, you can see it with the naked eye, and it's an amazing experience when you do. Even out west in North Carolina, it's difficult to see. It's just because the air is so musty and humid and nasty. If you are in really clear skies, not only can you see this band of light that covers the entire sky, which is our galaxy, we're embedded inside the galaxy, but you'll also see these black things. And this blackness in the plane of the Milky Way galaxy, it's not absence of stars. It is literally black clouds that block your view. And we call this stuff that's there that isn't stars, we call it interstellar medium. And for the purpose of this course, the interstellar medium consists of only two components. It consists of gas and it consists of dust. And I'll define those. Most of the interstellar medium is gas, but we talk about dust even though there's not a lot of it, because dust really, really absorbs light. And when you see these dark clouds, it's mostly that dust that creates those dark clouds. So gas is atoms, it's small molecules, it's usually hydrogen and helium. So, 99% of the gas that's into the interstellar medium, or the intergalactic medium for that matter, is hydrogen and helium. In fact, most of the universe is hydrogen and helium. Okay. Dust are particles that are a conglomeration of different atoms and molecules, such as this. Now, you think of dust as these particles, flakes of skin that float, and you can, if you get the light just right, you can see them floating around you. But those are huge compared to what we call dust. Okay, they are much, much smaller than the dust that we see in our atmosphere. But it's the same sort of thing. It's not a single atom. It's not a single molecule. It's a conglomeration, and most of them are very, very small. Okay. And when light goes through a dust cloud, what happens is the blue light is reflected, and what we see is the red light that makes it through. This, in fact, is exactly why sunsets are red, because the red light makes it through the thick atmosphere that includes a lot of junk. The blue light is reflected out of the way. And the same exact thing happens with these dust clouds, okay? If it's really thick, then we don't see anything at all, it's black. But if it's moderately thick, what it does is it reddens the light that comes through it. So the interstellar medium absorbs light more strongly at bluer wavelengths. And so when we look at it, the star produces, in this case, yellow light. The blue light is reflected out, and what we get is just the red light. Okay. So here is a really, really dark dust cloud, and you can't really see through it. But now we go to different wavelengths, and you can see what it does is it just reddens those stars. Okay. So 3 types of nebula that we're going to be talking about. A nebula is an old term. The term nebula was created back when we didn't even know what these things were. What percentage of gas and dust are we talking about proportionally? I don't know that for the purposes of the course and for the purposes of the test, the majority of stuff in the interstellar medium is gas. Okay. I don't know the exact percentage. So nebula refers to anything that's fuzzy that's that we see in the night sky. And the 3 types of nebula that we're responsible for, although there's lots of other types, is cold dust cloud, emission nebula, and reflection nebula. Notice there's multiple terms of nebula. Again, the bane of the astronomy existence is that there's multiple terms for the same concept, and there's multiple spellings for the same concept. And just to refresh your memory from a few lectures ago, there's 3 types of spectra that we talk about. There's continuous, the black body spectra that we talked about. And if we attach a spectrograph, then we see a continuous spectrum. And if we were able to get the proportion of those, it would be it would be that curve that you saw before. Absorption spectra is where light goes through a cold cloud, and because atoms are absorbed of particular wavelengths, we see those atoms of those particular wavelengths being absorbed. And so we have the continuous spectrum from the continuous source, and then we have the black lines from the intervening thin cloud that absorbs those particular photons. And again, this cloud has to be thin, because if it was thick, it would emit thermal radiation on its own. And emission spectra is where we have excited the electrons in a gas cloud, typically a hot gas cloud. And when those electrons drop back down to lower levels, they will emit photons of those particular frequencies. And as we talked about last time, those emission lines and those absorption lines match up exactly. Okay, so black body spectrum, absorption spectrum, emission spectrum. So here is the big thing, and this is on the formula PowerPoint that I posted when this class started. There's the processes that we need to worry about is thermal black body radiation, photon emission. When you've got a hot, thin body, a hot, thin, hot gas, that it's hot, meaning that the electrons have been excited, they're at a higher level, and when they drop down, they emit a photon. And photon absorption, when you have a thin, cold gas cloud and light, continuous light that is passing through that thin cloud, will absorb photons of those specific frequencies, because the electrons will be excited and go to a higher level, and they take a photon when they do so. Okay. So 3 processes and 3 types of nebula we talk about. A gas cloud, where we have atoms and molecules, lines are possible. I'm sorry, there's 2 types of nebula, and then we'll get into the next level. And then dust are particles. So gas consists of atoms and molecules, which can have lines, either emission lines or absorption lines, because you have naked molecules that can absorb or emit electrons. Dust consists of individual particles, and they can emit thermally, but they don't have any lines. And so that's one way to separate those. The types of nebula, as we talked about, the cold dust cloud, and if it's consistent of nothing but dust, then it can't have any lines. And what we get is when they're really thick, we get a thermal emission. But because they're really cold, that thermal emission is not visible. That emission is in the radio frequencies. And also it will reflect all blue light. And if it's not too thick, it will pass the red light. And so things that pass through the cold dust cloud that's not too thick will look red. If it's too thick, then you just don't see anything. Emission nebula is a thin hot gas because photon emission comes from thin hot gas. And typically it's hydrogen that's emitting the photons. And the nebula is hot because it's been heated and ionized by close, really hot stars, typically in the ultraviolet. And then a reflection nebula is kind of mirroring what we see with the cold dust cloud, and that a reflection nebula is, you remember all those blue photons that the cold dust cloud scattered? Well, if you look off to the side, you can see those blue photons and it looks blue. And so if instead of looking through the cold dust cloud, if the cold dust cloud is illuminated by a really bright source off to the side, we can see those reflected blue photons. Okay. So let's start with the cold dust clouds. Here you can see this is the Horsehead Nebula. It's one of the most famous cold dust clouds out there. I'll show you a little video of that. And here, this is the radiothermal spectrum for the cold dust cloud, showing that when it's really thick, it does emit continuous black body radiation, but in the radio waves. Okay. And again, here's other examples of cold dark nebula. Emission nebula, such as this. This is the Orion Nebula. We have hot stars illuminating the gas clouds. It excites and ionizes the gas, and the electrons then fall back down to the ground state and produces the emission lines. And the gas is thin, so there's no black body radiation. And it's red because the lines that hydrogen have emit mostly in the red. Okay, so again, you've seen this before. This is absorption. A photon comes in, and that photon is absorbed. So this is an absorption spectrum there. An emission spectrum is where the electron drops down, it emits a photon, and reduces a line. Absorption, emission, absorption, emission. And there are the different electron level lines, which you all learned about in chemistry. Is there a particular explanation to the Horsehead Nebula's shape, or that's just the way it is? I don't know the answer to that, Blake. My guess is that just the way it is. There's, it's just like, why is the shape of a seashore a particular shape? It's just the way it is. So that was cold dust clouds, emission nebula. Here's reflection nebula. This is a beautiful example of a reflection nebula. You have these very, very bright stars that are illuminating a thin a thin dust cloud, and we see the blue that's reflected from those thin dust clouds. Okay. Star illuminates a gas and dust cloud. The light is reflected by the dust, and it appears blue because the blue light scattered at larger angles than the red light. And there it is. So here's the star, there's the telescope, the red light makes it, the blue light's scattered away. So here we see a cold dust cloud there that's so thick it blocks all light, and there is where the dust cloud is thinner. We see the blue that comes from the reflected light. Now, what you're going to see is let me stop this. Oops. What you're going to see in the simulation next is there's a star that's pulsing. And to prove to you that what you're seeing are the reflections through that gas cloud from the source of the light that's hitting that gas cloud, we've got a star that's pulsing. And what you're going to see is the pulsing of the reflected light as the main star is pulsed. Okay, so there's the main star. And now the main star pulses up and down, and look, you can see the reflected light as those pulses of light transfer through that big cloud. Okay. That's just an amazing video. So dark nebula and reflection nebula are just the same thing from different angles. For the most part, yes. To what extent are these photos interpretive in terms of coloring? I'm referring to the technical process of producing these photos. This question might be misplaced. No, Cole, this is not misplaced at all. Geez, I'd refer you to my book on human color vision. The problem is that we interpret colors based on the red, green, blue sensors in our eye. Typically, photographs, especially from the Hubble, are taken at different frequencies than red, green, blue sensors of our eye. And so what they try and do is modify the colors of that so it closely matches what we would see. The problem is that phrase, what we would really see, doesn't really operate. And the reason why is because our brain is continually adjusting the color of things that we see, trying to figure out what white really is. So if you use an old-fashioned film camera and you shoot indoors under incandescent light, everything is red. And then you go outside and everything looks blue, and you go under fluorescent light bulbs and everything is green using an old-fashioned film camera. But that's not the way it appears to us. To us, everything appears white. You know, inside doesn't look any different in terms of the overall color shading than outside than under fluorescent bulbs. And that's because our brain has this feature called color constancy, which is it's always continually modifying. And so when we say, what would it really appear to be? We don't know, you know, because as we get to interstellar space and we're looking with the naked eye at these nebula, how is the brain going to interpret that? And what kind of colors is it going to think it really is? So I can tell you in terms of the actual physical spectra, but I can't tell you how the brain's going to interpret that. So it's kind of weird. So are those shock waves? So Louise, they're actually not shock waves. I mean, there are great examples of shock waves in the future that we'll be talking about in the future. What are these? Are just light reflections. What you're seeing is just the reflection of light, and because the star is pulsing, we're seeing those reflections of those light. What causes the star to pulse? So Art, we'll be talking a little bit more about that in lecture on Tuesday. But basically, it's instabilities in the sun. And some of those pulses, some of those Cepheids are very important for us to figure things out. Does the star actually pulse? No, that is not an illusion. The star is actually pulsing. Lots of stars are variable. In fact, our star is somewhat unusual in that it doesn't pulse. Okay. So here is a graphic that kind of illustrates everything. We have an emission spectra that's heated up by hot stars, and the re-emitted emission light is sent out as red light. Then we have visible starlight that hits a dusty cloud, and through the dusty cloud we have red light or no light if the dusty cloud is really thick, and then the reflected blue light here. So that's a reflection nebula, and this is a dark dust cloud. Okay. Can stars collide? Yes and no. So our star is a few light seconds across, and stars typically, the distance between stars out where we are is of the order of light years, which is, was it 7 million seconds? So we've got a ratio of millions to 1 in terms of the diameter of stars to the distance between stars. And so normally no, stars can't collide. That said, there are places where stars do collide. And one of those places is centers of galaxies, which we'll be covering much later in this course. And in those cases, yeah, stars do collide. And in fact, in 2015, we heard through LIGO the collision of 2 neutron stars. The collision of 2 neutron stars generated more energy and gravity waves when that collision happened and during that collision than all of the energy produced by all of the stars and galaxies in the universe at that time. It shook the fabric of the universe. And so stars do collide, but it's rare. I'm still unclear what I mean by reflection. What we mean by reflection is the light comes through the dust cloud. It is reflected off of those dust particles, just like a mirror reflects. Okay, a mirror takes light that's traveling in one direction and puts it in a different direction. That's exactly what the dust cloud does. It takes light, blue light that's going in this direction, and it reflects it. It makes it go in a different direction. Whereas red light is not reflected. Red light goes through. What is the closest nebula to our system? I don't know. I'll have to look that up. Getting off, what if a star crashed into the sun? It would be a very bad day. It will not happen. What remains of the two stars after they collide? Taylor, hold that thought. When we talk about colliding stars, when we talk about black holes and neutron stars, we'll get into that in some detail. And so there is that picture we started with: the reflection nebula, the dust cloud, and the emission nebula in a single image. These images are just beyond amazing. Okay, and so here is the Horsehead Nebula, the dust cloud, and we're going to take a trip to it. Now, this is actually not an actual trip because we can't send space probes there, but we have very high resolution images of this area, and we know the distances. And so this is a pretty good, accurate representation of what it would look like. Stellar nurseries. These are called the Pillars of God. It's one of the most famous Hubble pictures. A stellar nursery is where there's so much gas and dust in one place that eventually it will collide and form stars. Now, usually the gas and dust, even though it's really dense, it's not dense enough to start collapsing based on its what we call self-gravity, the gravity of the dust and gas itself, just because gravity is a very weak force. So typically what it needs is it needs something to get it started. And typically what gets it started is a shock wave, where there's a blast of stuff that pushes it really hard. And more often than not, that blast of stuff that pushes it really hard is going to be an exploding star, a supernova. Okay, and that's what gives birth to stars. And so star formation can happen either by the death of a nearby star that sends spewing stuff out. Supernova creates these incredible explosions and shock waves, which will compress these gas and dust clouds, or galaxies collide and produce the gas and dust from the two galaxies will smash into each other and greatly increase the density of the gas and dust clouds, and those gas and dust clouds will collapse onto themselves. And as they collapse onto themselves, they produce what we call protostars. They produce a disk of stuff. And here's some examples of that, some pictures of these protostars, and I'll show you a visualization of that. Okay. And as we go from, and notice that they collapse into a disk, and as we showed you last time, when they collapse into a disk, that everything is in a disk. The solar system is a disk. Saturn's rings are a disk. Our galaxy is a disk, just because the universe likes disks. It likes collapsing stuff into a single rotating plane. Okay. If there were a supernova system near us, would we feel it, and what would we feel like when we do it? Hold that thought. We will talk about that in some detail, because Betelgeuse is doing some very weird things. Betelgeuse might very well go supernova in our lifetime. Do any stars have rings? Yes. In fact, almost all protostars have rings. And we're going to go back to the Hertzsprung-Russell diagram to talk about stellar birth. And remember, here is the Hertzsprung-Russell diagram, the temperature on the bottom, luminosity along the x-axis. Here is the main sequence, cooler stars on the left, hotter stars on the right. And here are the different regions. So main sequence is where 90% of the stars are. The giants and supergiants are where stars go when they die. And we'll be talking about that in a future lecture, and certainly white dwarfs. So again, these outliers are for dying stars. Nowhere on this graph do we show how stars are born, and that's because stars are born very, very quickly. And so we typically don't see them when we look at the night sky, because they just are born so quickly that they just don't stay around very long. All protostars will then quickly go to the main sequence, and they'll spend most of their life in the main sequence before going off the main sequence as they die. So here is, this dotted line is the path that stars follow as they're born. They start off with almost no luminosity and no temperature out here. And as they collapse, the luminosity goes up and the temperature goes up. Why is that? And that's just exactly what happens in your diesel engine. In a diesel engine, you get gas and you get fuel and air, and then the piston comes up, rams into the cylinder, and as it rams into the cylinder, it compresses that gas and dust. And when that gas and dust is compressed, it heats up. And eventually it gets to the point of a few thousand degrees where it ignites and pushes the piston down, and you get a diesel engine, and you go off and drive your truck. Same thing happens here, except instead of this external force of the piston pushing up, the force that's compressing this gas and dust is gravity itself. So gravity of the gas and dust is pushing that gas and dust, so it's denser and denser. And as it's pushing it, it's getting hotter and hotter. And as it's getting hotter and hotter, the luminosity goes up higher and higher until it reaches this high luminosity, and then it continues to get hotter as it gets smaller and smaller, as it continues to compress. And as this compression happens, in a diesel engine, I don't know what the ignition temperature is of fuel air mixture, but let's say it's 1,000 degrees. When it hits that ignition temperature, the diesel engine, the fuel air mixture ignites and the diesel engine moves. Same thing happens in stars and protostars, except here what we're talking about is the ignition temperature of fusion reactions. And that would be at the core of the sun. And that ignition temperature for the first reaction, which is the proton-proton hydrogen to helium fusion reaction, is 10 million degrees. So, and that happens at what we call the birth line. So here are the birth lines for stars of various different masses, okay? And when it hits the birth line is where the core of that sun, of that protostar, reaches the fusion temperature, which is around 10 million degrees, and fusion starts. And our definition of a star is where the energy source is fusion, not the gravitational contraction. In fact, we knew in the 19th century that there must be something like nuclear fusion, because we calculated that if the star was driven solely off of either chemical reactions or just gravitational contraction, the star could only be a few million years old. And we knew that the Earth was hundreds of millions of years old. So we knew that there was something we didn't know. Just like right now, we know that there's something we didn't know. We know that dark matter and dark energy are things we do not know. So the first step in understanding how much you don't know is first understanding that there are things you don't know. And then you can try and figure out what that is. Notice here that the place that the star winds up is proportional to its birth mass and nothing else. So the place on the main sequence is proportional only to its mass, not really to anything else. And so the mass on the main sequence goes from small mass to big mass. And what happens to you depends almost solely on your mass. The most important thing about you is your mass. Nothing else matters. Doesn't matter what your eye color is. It doesn't matter what your IQ is. Doesn't matter what your hair color is. All that matters is your mass. Imagine if human civilization was like that. In other words, my mass would mean I am a certain type of person, and your mass means you're a different type of person. And everybody that has your mass has exactly the same past and the same future. That's the way it is with stars. Mass is everything. Are you calling me fat? Well, I can't call anybody fat, Matthew. I'm bigger than all of you. Circle of life. So here's the thing. Supernova are the end of the life. And we'll be talking much more about this in later lectures. And when a star explodes, the supernova produces the shock waves that compress the gas and dust cloud to produce more stars. And some of those stars will blow up. And when those stars blow up, they compress more gas and dust, which produce more stars, which blow up. And so we have this circle of life, just like we do in biology, okay? So in stars, which we'll be talking about in future lectures, after the exam actually, stellar death is really important. Unlike in humans, when people die, we're sad and we bury them. But imagine if, when somebody died, it blew up and took out a city block. I mean, death would be very important. And here the analogy breaks down, because that person blows up, takes out a city block, and then there's bursts, babies are born around that explosion. I mean, the analogy breaks down. But that's the way it is with stars. That stellar death is a very important part of stellar life. In fact, it's typically the cause of stellar birth. So sources of stellar energy, I mentioned that there's really two types. There's hundreds of different ways that atoms combine to form energy, fusion energy. The one on the left is the most important for the sun. The one on the right is the most important for stars that are a little bit more heavy than the sun. And let me show you a couple of. So this is called the hydrogen to helium chain, or the PP chain, the proton-proton chain, and this is known as the CNO cycle. So let me show you some simulations of that. Okay, it's a new share. Okay, so here is protons, neutrons, and positrons. A positron is an antimatter electron. So let's start the animation. Two hydrogen atoms combine. One of those hydrogen atoms, atoms combine. One of those hydrogen atoms turns into a proton, and a positron split off. Another hydrogen atom comes along, combines with that, and now we have helium-3. Helium-3 is we've got two protons and one neutron. That happens at both top and the bottom. And then those two helium-3 atoms combine. A couple of hydrogen atoms split off, and we wind up with hydrogen-4. So we start off with six hydrogen atoms, and we wind up with one helium-4 atom and two hydrogens. So the net result is 4 hydrogens go to helium-4. And in this process, we generate a lot of energy and also a couple of positrons. Okay. So, and here the energy is taken off in the forms of gamma rays. So this looks like complex, and it is, and it's by far the simplest fusion chain that exists on the surface of the sun. There's a story about Hans Bethe, and we knew at the beginning of the 20th century that our sun had to be driven by fusion power. We understood a little bit about fusion, but we didn't understand the details. And in particular, I'm going to show you the CNO fusion cycle, and you can see how complicated this is. And again, you're not going to be responsible for the details of this, but I just want you to get a concept of how complex this process is. Okay. And again, this is one of the simplest processes, and there's hundreds of these different processes in stars. And in fact, one of the centers of research into this stellar nucleosynthesis, they call, is here at both NC State and at UNC. What is the definition of antimatter? Brody, antimatter is like matter, but all the signs are flipped. So a negative signed electron is a positron. There's antiprotons, antineutrons, and so on down the line. We know that they exist. We can create them in supercolliders. And when an antimatter atom and a matter atom touch each other, they are both annihilated and produce nothing but light. Why does it exist? We don't know. That's just the way it is. If 12C is a product of the chain and also starts the chain, where did it come from in the first place? So Matthew, that's a really good question. The reason where it comes from are other processes that are not on this chart. Okay. Like I said, there's hundreds of these different processes. Let me get back to Hans Bethe. So this was an unsolved problem. We knew that fusion happened, but we didn't know the details of fusion. And again, you can see how complicated this is. Well, Hans Bethe was one of the people trying to figure this out. And while he was trying to figure that out, one night he had this flash of insight. And his flash of insight was actually this exact process, which is complicated, but it all kind of works. And he was out strolling on the night with his girlfriend, and his girlfriend looked up at the stars and says, "Look, the stars are so beautiful tonight." And Hans Bethe turned to his girlfriend and says, "Yes, they are beautiful. And right now at this very second, I am the only person on the entire planet that knows why they shine," which was true. So anyway, let's go back to this. And how do we know the details of this? Again, because in some ways the stars are relatively simple. We used computers and the equations of thermodynamics to calculate the pressure and temperature and density at the center of the sun. And then given that pressure, temperature, and density, so in this particular model, the center of the sun of this star is at 15 million degrees. And we know at 15 million degrees and at that particular density that these fusion processes will continue. Okay, and so the laws of stellar structure is hydrostatic equilibrium. Every layer has to be in perfect balance. If they're not, things will move. This is obviously true with the Earth's atmosphere. If there was a big bundle of air that was very dense and was very high, it would have to fall. And in fact, that motion to maintain hydrostatic equilibrium is what creates weather on the Earth. Energy transport, the energy that's created at the core, has to make it out to the surface of the star. And it has to make it out so that the amount of energy generated must equal the amount of energy that's expelled, or energy will build up in some intermediate layer. And so the fact that energy transport has to be balanced at every radii really helps you understand how stars are. Mass conservation, the total mass of all these layers has to equal the total mass. And energy conservation, the total luminosity equals the sum of the energy per second in all of the layers. All of the layers must be able to transport or generate the same amount of energy. Okay. And we'll finish the lecture with a trip to the Orion Nebula by Leonardo DiCaprio. I actually know the people well who made this video. I don't know Mr. Caprio, but I know everybody that the team that made this video at the university. Okay, let me work on the sound. Hold on a second. Oh, sorry about that. Okay, let me kill that. That was my mistake. You can hear me now, right? Okay. Sure.
This is real star travel. The bright star passing by.
We still have motion of particles. They're pretty rarefied, but it's still a motion of particles. And so those tadpole objects are caused because there's a stellar wind coming from these really hot young stars of particles spewing at very, very fast velocities that push things away. So, you know, there's no air in space, and actually that's not strictly true. There is air, but it's a very unusual air. It's air made not of nitrogen and oxygen and carbon dioxide. It's air made of mostly hydrogen and helium. And you have a density that's a trillionth the density of air that we breathe, but it's also moving very, very fast. And so on cosmic scales, we do see these things that you see in the air. You see these shapes that are bent down, okay? And in future lectures, you'll see supernovae that blow up that produce these shock waves that have massive changes, massive disruption as those shock waves permeate through the area around them. And then, of course, we have neutron stars and black holes and gamma ray bursts, all these things that really do extreme violence to the universe that we'll be talking about in a future lecture. Boneless air, yes. I'd watch a full Leonardo DiCaprio space voyage. So this is a clip from a IMAX movie called Hubble 3D. Virtually all of the, in fact, I have a cute little, well, not cute, a story to tell you. The team that did this at Illinois I had a celebration that I organized a couple years ago, a celebration of the team and all of the Space IMAX movies that they made, and we invited the producer of most of those Space IMAX movies to the thing, and I met her when I was waiting for my a flight at O'Hare. And she and I got to talking, and we're saying we're going to the same festival, the same celebration of IMAX space movies. And she was older, and while we were talking, she got a call on her cell phone, and she walked away from the from my conversation. When she came back, she says, "Oh, that was someone wishing me a happy birthday." And I says, "Oh, that's nice, happy birthday." Turns out the person that called her when she was waiting for me for a flight at O'Hare, the person that called her was the commander on the ISS. She got a call to wish her happy birthday from the ISS because she had trained all the astronauts on how to use those IMAX movies cameras. Anyway, do we know where the sun was born? Yeah, the sun was born where it is now. It hasn't really moved a lot. We're kind of on the, as we talk about the Milky Way galaxy, we'll talk about this, but we're kind of not really in the suburbs. We're kind of in the exurbs of the Milky Way galaxy, and that's where we were born. Things have changed, but not a lot. We're only 4 billion years old. Are there other gases besides hydrogen and helium in the winds? Are they the only ones? Yeah, so there's a whole bunch of different gases in that solar wind, but hydrogen and helium is 99%, and then there's the other items. So when the universe was born, it was all hydrogen and helium. There was really nothing else. And so the very first stars were formed only of hydrogen and helium, the very first solar systems. And so at the very beginning of the universe, there were no planets, because planets are made of things other than hydrogen and helium. So our star includes a whole bunch of other atoms in it that were not formed in the sun. They were formed from previous stars, like the CNO cycle, the carbon, nitrogen, oxygen that you saw. And all the other elements were formed in other generations of stars. Our star is probably 4th or 5th generation. And that's why the planets exist, that we exist. We're made, of carbon and nitrogen and iron and a whole bunch of other stuff. And those are all the results of previous generations of stars that blew their guts through the universe, through these solar winds, and were caught up in the sun and the planetary systems. And so if it wasn't for those other stars giving their lives, we wouldn't be here. Anyway, that's the end of the lecture. I'm open for questions. You're free to open up your mic. If I ever make it to the ISS, I'll be sure to phone you. Thank you, Joseph. I would love to. And don't forget Christina Cook, the alumni from NC State Physics, who just got back from the ISS. She was just quoted in Smithsonian Magazine saying that she found the COVID virus more lonely than it was in the ISS. And remember, she holds the record. She spent the most time in space of any American female. How does life differ on the outskirts of the galaxy as opposed to the center? So Brody, that's an interesting question, and we'll be covering that in the very last lecture of this course, when we talk about habitable zones. There's habitable zones around stars, and there's also habitable zones around galaxies. And so we don't think that life could exist in the center of our galaxy, and we don't think life could exist in our farthest reaches of the galaxy. What is the oldest star that's still living? So the stars that are those small red dwarfs that we call them at the bottom of the main sequence, they will never die. I mean, their lifetime is in trillions of years. And so there are stars that I think we've found stars that are as old as 12 billion years old. And remember, the universe is only 13.7 billion years. Could you talk about the James Webb telescope compared to the Hubble telescope? Yes. So the James Webb is, dozens of times larger than the Hubble telescope. There's two things that are fundamentally different about the James Webb. Well, three things. First of all, it's much, much larger. And so it can collect more light and has more resolution. The second is the James Webb telescope is not an optical telescope. It does not take pictures in light that we would see with our eyes. It takes pictures in infrared. It does that for two reasons. First of all, infrared is longer wavelengths, which means that the mirrors can be made with somewhat less precision. And when you're making something that has to fold, that precision is important. And the second is that because of Doppler shifts, the things that we most care about to observe, the things that are in the farthest reaches of the universe have been Doppler shifted to the infrared. And so infrared is where all the action is, and that's why James Webb is infrared. The other thing that's really scary about the James Webb is the Hubble telescope was in low Earth orbit. Which meant it had to be boosted every so often so it didn't fall towards the Earth, but it also meant it could be serviced, and it was serviced 6 times in its lifetime, and it's still working. The James Webb will be at L1. It will be, I'm sorry, L2. It will be 1 million miles away from Earth. It cannot ever be serviced, and so if anything goes wrong, that's all she wrote. And it's, what was it, up to 20 billion now? I forget. Anyway, it's the price tag for the James Webb is astronomical, and I just find it kind of scary. I think it's too big for its own good. What happens if all the hydrogen fuel in the universe gets eaten up? Then the universe ends. And so, Joseph, what I would recommend doing is check out a book of my colleague, and actually the person who, not next semester, but teaches this course. I alternate this course with Dr. Katie Mack. She just wrote a book called The End of the Universe. It was just reviewed by the New York Times. I would recommend picking that up if you're interested in that question. Do you think commercial space flights will exist in our lifetime? Well, they already do exist. I mean, as astronomers, astronauts go to the ISS on a commercial space flight now, on that SpaceX. When will the ISS fall back to Earth? The ISS is periodically reboosted, and so when the ISS is abandoned and they stop reboosting, I don't know when it will fall back. My guess is it'll have a lifetime of maybe 5 to 10 years. Do you know her? Yes, I do. I met her several times before she went into space. You know, she, not only is she an alum, but she actually grew up in Raleigh, and so her family is here. Her best friend of all time is the wife of a colleague of mine, and so I got to meet her several times. She's unusual. I mean, I understand why they chose her as an astronaut. She chose to live at the South Pole for years at a time, working on the South Pole telescopes there, and then she worked in the outback in Australia at a remote outpost. I mean, she is beyond a serious athlete. She's a climber too. She makes a perfect astronaut. I wonder how fast the internet is on the ISS. Yeah, so that is a good question. And the problem is that they have to shift their internet service every couple of minutes as they pass around the Earth. Now they also use the Tertis relay satellites, but still there's a lot of very complex moving of the signals as they go in orbit between the Tertis satellites and the ground stations. And I know they sometimes complain about that. Would you consider making an astronomy podcast if you had all of us dedicated listeners? You know, I've been thinking about that. I have the equipment now. Are there stars other than the sun that are close enough that they explode, they would impact our solar system? We don't. So, Sophia, that's a good question. We don't think so. We think that the danger radius is about 50 light years. Betelgeuse is about to blow up, and it might very well blow up in your lifetime, and that would be a spectacular supernova explosion. It's 700 light years away, and so it'll be a spectacular in the night sky, but it's not going to cause us any danger. But if we were closer to Betelgeuse and it blew up, it would be a very bad day. Now, we do think that a close supernova did blow up about 3 million years ago, because we see the radioactive isotopes in cores, and we think that there was a minor extinction of life on this planet due to that. Some people postulate that a close supernova really caused one of the major extinctions several 100 million years ago, but there's a lot of debate about that. How dense exactly is the interstellar medium? We usually think of space as a vacuum. So it is incredibly, incredibly thin. So it is, even in the densest part of the interstellar medium, it is thinner than any vacuum we can conceive of on Earth. So typically every centimeter of air that we have has on the order of 10 to the 23rd power particles in it, Avogadro's number, 10 to the 23 particles in every square centimeter of air. In interstellar space, even in the densest part, typically there's one atom or one molecule, 1 versus 10 to the 23. 10 to the 23, that's 1 with 23 zeros behind it. So it is incredibly thin. What would happen if fusion slowed in the core of a main sequence star? Here's the thing, Ward, our simulations are so good that we know that that cannot happen, okay? We know, and in fact, the opposite happens, and that's why stars evolve off the main sequence. The fusion actually goes into runaway mode, and we'll be talking about that when we talk about the death of stars. And if our models were wrong, we would see it. And remember, we can observe billions upon billions of stars out there. And if anything's doing anything weird, we would know it. And we've never seen a star where fusion just dies, okay? I mean, for regular people to pay to go on a space flight, that's already happened. We've had probably a dozen, maybe a couple of dozen people who have paid for a space flight. In fact, I was in a car, an SUV, driving to a telescope in Chile. We were going to have an opening ceremony for this telescope. And I was in the van, and I was sitting next to a guy who was, we were talking about flying, and I says, you know, I've got a plane. And he says, yeah, he's got a plane. He flew down to Chile in his Jetstar. And I says, oh. He says, yeah, I've got the Jetstar, and then I've got an F5. I use the F5 because I'm training to go to the International Space Station. I say, what? Turns out this guy, he was one of the founders of Microsoft. Simone, Charles Simone. He went to the ISS twice. He paid for it. He paid $20 million per trip. And so we already have, and what you're talking about is, you know, normal people who only pay $100,000. Well, you'll be able to do that on Virgin Galactic next year. So, I mean, it's already happened, slowly, but it's happened. How close would a supernova have to be to Earth for there to be adverse effect? About 50 light years. Where would Betelgeuse have to be in the main sequence before it went giant? So Betelgeuse is in the really upper reaches of the main sequence, you know, towards the O range. So O, be a fine guy, kiss me. O is the hottest and the brightest, and Betelgeuse is up in the OB range. Other questions? Okay. I will see you next Tuesday. Remember to vote. It's the most important thing you can do this semester, other than, of course, enjoy this class. Thanks so much, and I'll see you guys on Tuesday.
I'm left, I mean. Hey, bye, Brand.
Bye-bye. Thanks so much.